am going to explain acceleration diagram of slider crank mechanism using the relative velocity method. Let us see the problem. In a slider crank mechanism, the length of the connecting rod is 160 centimeters and the crank is 48 centimeters long and rotates at 20 radians per second in the counterclockwise direction with 5 radians per second square angular acceleration. When the crank turns 60 degrees from the inner dead center, determine the acceleration of the slider. Now we are going to find out what is the acceleration of the slider. Now we will see that the construction of the velocity diagram and the configuration diagram that I already explained in the previous video. You may watch that video, velocity diagram of slider crank mechanism. Now I am going to explain directly the acceleration diagram of the slider crank mechanism. So before going to draw the acceleration diagram, first of all we need to find out all the vectors, magnitude, the direction, sense, so that it's easy to construct the acceleration diagram. Now you can prepare this tabular form and you can find out all the values. Now the first acceleration of B with respect to A. So the type of acceleration is the radial acceleration. The vector representation is f of B with respect to A, that will be represented as A1 x bar, and magnitude is VBA whole square by BA, and VBA is the vector AB. So the vector AB value you can take from the velocity diagram and square that value and divided by the length of the AB, that value take from the configuration diagram. And the direction is it's parallel to the link AB, and since sense is toward the center of rotation, here the center of rotation is A, so now it's moving from B to A. Okay, so the complete information is available. Next, go to the next component, tangential acceleration. It's representing the FBAT. It's is equal to x, vector representation is XB1. So combining these two vectors, you can obtain the A1 to B1. So the magnitude is alpha into AB. Alpha is the angular acceleration of the link AB, and AB is the length of the link. And direction is perpendicular to AB, and sense is in the direction of link rotation. So with the information complete, you can construct the vector A1, B1. Next, coming to the next, the velocity acceleration of the point P with respect to B. It's also having the two components, radial acceleration and tangential acceleration. The radial acceleration is representing the B1y, and the magnitude is V square PB by BP. That is a BP vector you can take from the velocity diagram and find out the magnitude of this vector, and the direction is it's parallel to BP, and the sense is towards center of rotation B to the P. This gives the complete information of the radial acceleration component. Then tangential acceleration. The tangential acceleration of P with respect to B is representing the vector YP1, and the magnitude is unknown. Direction is it's parallel to the because it's a tangential acceleration, it's a perpendicular to the link BP, and the sense is also unknown. Next, assuming that the point P lying on the slider. Okay, now the slider is moving only in the linear motion. The slider is moving in to and fro motion. It's linear motion. In this configuration, the slider is moving in horizontal direction. So it's having the total acceleration becomes only the tangential acceleration. Here the centripetal acceleration is 0 because the slider is not having the rotary motions. The vector representation is it's a final vector A1 P1, that is a tangential component of P with respect to A, and here also the magnitude is unknown. The direction is it's parallel to the path of the slider. In this case, the path of the slider is horizontal, so it's parallel to the horizontal, and the sense is also unknown. So with this information, we are going to construct the acceleration diagram. Now see the configuration diagram and velocity diagram. Okay. Now we are going to construct the acceleration diagram. First, mark the point and assign the fixed points in the mechanism. In the fixed point is A, then you can mark this point as a A1. Now draw the radial component of B with respect to A. So that is the A1x. This vector is FBA, the radial component of acceleration of B with respect to A. Now draw the tangential component that is perpendicular to this vector. It's representing the FTBA, that is the vector XB1. Now once A1, B1 is known, join these 2 points. It is the total acceleration of B with respect to A, that is the FBA. That is the A1 to B1. Next, find out the radial component of P with respect to B. Now draw the vector from b1 to y. So this vector is the centripetal component of p with respect to b. Next, draw the tangential component which is perpendicular to this vector, that is the tangential component of p with respect to b up to certain length. The length is unknown, up to certain length you can draw. Now assuming p on slider, and slider is having only to and fro motion, so that is a tangential acceleration is the final acceleration of p with respect to any fixed point. So now from the A1 you can draw the line. It's a solid line because it's representing the final the acceleration vector. So the intersection of these two lines is the point P1. Okay, so once the P1 is known, then you can join A1 and P1. It's representing the acceleration of P with respect to A. Then you can join B1 and P1. It's representing the total acceleration of P with respect to B. So this is the required acceleration diagram. So in this problem, you need to find out the acceleration of the slider. The slider acceleration means that point P. Now you can measure the vector P1 and A1, that is FPA. This vector directly gives the acceleration of the slider. Okay, so whatever the scale you have taken, with that scale measure that value and multiply with this scale, then you can obtain the acceleration of the slider. So this is the construction of the acceleration diagram. I hope all of you understand how you are going to construct the acceleration diagram. Okay, thank you very much.